the material and process specifications. That was from Monday, and there's a number of reasons. The first one is it is very important. Right? If you're gonna ask for a prototype to be built or a component to be put up there, it needs to resist corrosion in a certain way, it needs to resist mechanical strength or cracking resistance, then there's a lot that you can do to make sure it's going to be as good as the one that was built before, or if it's something completely new that is built to what your expectation is. People don't read your mind. I think we all learned that. So we're going to talk a little bit about weld quality with respect to application. I've got an example there. And then demand capacity, I wanted to talk about it in the context of these little engine turbine blades. So I brought those. And then we'll talk more generally about factors of safety, how you can end up with a design that is safer or not as safe as the previous version, or if it's something completely new, how you go about thinking about the requirements. So I mentioned about the welding code for structural steel, that this is it. This is the one that's got the sections on design of the connection, and then it will go through qualification of the procedure that you decide, the welding procedure. It will also go through the qualification of the welders that are doing the work. So if somebody comes and say, I'm welding for AWS, the welder himself is going to have a certification card, and the inspector also, if it's a certified inspector, is going to have a certification, a little stamp and all that to say that they understand this. And there's a lot of information. Some of it is annexes that are, some of them are for help, some of them are part of the code. So it's a whole 2-3 days of training to go through this. But I think that the bottom line, I think it's actually a good reference to think about what is involved with material and process specification, because that's what they do here in a very specific context of welding structural steel. And this is one example here. They will tell you a little bit about the kind of geometry of the weld that is acceptable. So if you have, you're making a fillet weld. A fillet weld is essentially when you have two pieces that are perpendicular. Yes, so for those of you who came a little tight, I did bring the example of the lap joint, and you can look at it after. We already circulated it, so we went through that, and it's essentially talking about whether you have bonding or not. If you have bonding, it's actually a very matte surface as opposed to a shiny surface. Okay, so we're just making here a T-connection, and we decide we're going to do a fillet weld. So the code will tell you, at the very minimum, it will say you can't have a weld that will look like this, because that over here, if this is the weld metal, it means that you didn't have good fusion. It's essentially that the melted steel was not comfortable on the piece of original material. So if we were to do a detailed metallographic examination here, we'll find that it's not bonded. It actually has some example of that. So what the code says with this schematic here, this table, is it establishes kind of a maximum and minimum convexity for that surface. You can have a concave weld, but if you do, a lot of times it's associated with undercut, so you're going to have less material here. And depending on the quality requirement you have, that may or may not be acceptable. So most welds have a certain convexity. If you go to just the gym and you look at all the equipment that's out there, typically it's actually pretty rounded beams. And the reason is they use tin metal, relatively thin metal. They're not welding something that's a quarter inch or an inch thick. You're dealing with something thin, and if you heat too much this base material, you're going to have a burn through. So you want to be more in a condition of convexity, but not too convex like I did this one, where you're actually not fusing with the base material. So it's by far the most common problem with just typical structural wells, like a fusion. They go and they don't heat up enough the base material so there is no connection between them. And what the code tries to do, just by, because I'm saying here the proof is if you cut it up, well, they don't want to do that. So there's essentially some criteria here to look at the shape of the bead to try to essentially identify this as a potential problem and avoid a failure. We had snow this year, but we also had snow last year. No, and I think the last big snow was 2011. In 2011, I probably had to go on 20 roofs because I was working for a structural and they were having issues with the roof joists. And the basic story there with roof joists is they are not required to meet this code. They're not inspected by certified welding inspectors. They do have welding specifications, and it's written down in somewhat similar way. They'll say you don't want lack of fusions, but they don't have the criteria on the surface that we've talked about here. These are not included in that spec. So it's more of a performance-based spec where they do what they do with quality control. They take the entire joist. Oh, by the way, so the joist is essentially if you have two main columns on the building, you have trusses and joists. Joists are what you see, if you go to Costco or any big department store. So it looks like this. It's got a lower flange, it's got a top flange. So these are chords, and the diagonal is what's connecting them together. It's a very, very typical roof structure because it's very economical to make. So every single one of these joists is required to resist a certain amount of load. So what they do, according to the Steel Joist Institute, which becomes a little bit the equivalent of the Copper Development Association for this application, is they say, okay, just load some joists and prove to me that they're strong enough. The problem with that is you don't do it for every joist. So if there is variability, if you hire some new welders, if everything now is done outside the country, then you may be getting very different detail of your welding, and it would be great if you had more of a specification and a quality assurance program for these geometries. So what happened in this case, this was a 20-acre greenhouse. They were growing tomatoes in Maine, and the building was up for about 2-3 years, and they had a big snow, the first big snow. And the way these are intended to work is they heat enough the greenhouse that they melt the snow as it falls, so they can keep getting the natural light through the winter. But snow was falling too fast, so they did have a snow load. And the design, which was from the Netherlands, wasn't all that clear about what it will be able to resist or not exactly. We think of roof loads in pound per square foot, and there's very specific requirements depending on where you are in the U.S. for how much you're supposed to take for that snow load. Typical would be 30, 40 pounds per square foot, so it's a fair amount. If you're looking at a reception room, just the floor of reception rooms, they say 100 pounds per square foot, so you can't stack that many people in one area. So that's a little bit how these are built in terms of figuring out your demand. So in this case, they had these joists, a lot of them. There was probably 3,000 to 4,000 joists like this. you see them going from the columns. So this is a slightly different design than this one. It actually continues on here. So you have the lower chord here, the upper chord, and that's going from one column to the next one. Pretty long choice. The detail of the diagonals, you can see the way you do this back and forth pattern was just with a round bar. So this was essentially just a rectangle tube. And then on top of it, you had a bar. So the bar on this plane was essentially laid out bent and bent. So you have an area where it's following the beam at each end, and you can weld on. So on the plane view here, you essentially will have it on top right here. So you're trying to weld between something round and a flat surface. And it didn't work too well. And based on what we already discussed, you can probably see here, this is very convex. So the weld did not really go deep into the material, and therefore, when it failed, you pretty much go back to the original shape of that tube, and all the weld metal went with the bar. What does that mean? It means that when the welder came here, he knew that this was going to require more heat to melt it, so he just went on and put all the heat there, and he fused with it, but he did not fuse with the rectangle down there. It was more just a very low quality braze joint without flux, very low strength. It holds there kind of by mechanical interlocking. So this is essentially a cut view of the weld of this detail, and I have a good weld. This is very rounded. This is the fusion. So this is essentially the weld metal plus a little bit of that tube that has just got mixed by the heat of fusion. This is an all arc welding. Over here, you can see this is an etched microstructure, and you can still see the line, especially here. There's actually a gap between the original tube and the weld metal. So it just wasn't fused, and that's an area where it will start to crack very easily. So the bottom line again is, what would you expect if you say, I want you to weld it to a certain size? Perhaps this meets your size requirement, but it doesn't mean what would be the other kind of very basic requirement, fusing all components. That's why we do fusion welding. But they had, this image is actually not from the original choice. These were replacement choice. That they knew they had a problem, and they were coming back to do them very well. So what the process is there is you can still tolerate, because you got so many of these joints, right? You have one here, you have another one there, you have so many of them. So the idea that you have one bad weld on one side, because these are all working together, this one and this one, the bar is running this way, is acceptable. But it does become a question of proportion. How many of these are you going to tolerate? And if we were in the shop, seriously, you just ask the guy to redo this one, and he's gonna, next time he's gonna, pay more attention, probably even do it himself. The problem when it's all installed, especially, is it did have a galvanizing and a protective coating, so the idea to come and just spot repair something is very, very expensive up there. So on the first time around, what they wanted to do at first, they didn't want to stop production, so they wanted to go back up and repair it. And I'm bringing this image just to give you an idea of what it should look like. It doesn't look as pretty, perhaps, as the welds that you see on the exercising fitting equipment. It's just very nice and smooth. So these ridges here, you can expect them. That just means that it's the progression of the weld pool as you move forward. If you go really fast, sometimes you don't see those lines, but the idea of going fast a lot of times does mean less heat input into your base material, so it looks great. but it's not really fused. So this was actually one of the best quality in terms of strength, but it does have a little bit of a rough appearance. So the main thing to think about quality of welds is, do I have fusion and do I have contamination? If for some reason they didn't supply, for example, gas shielding, if you're supposed to shield here, or they didn't remove all contaminants, rust, all of that before they start welding, that's where the main problems are, typically, as opposed to exactly how it looks like, is it smooth and all that. So they wanted to do that at first, and then it was really going to be too long, too expensive, even though they did have tracks to collect the tomatoes, so that we could go up there pretty much with the standard equipment and they had in the facility. But it was going to take too much time, so the one that you've seen an image of is new joist that got delivered, 3,000 of them or so, and because of the problem they had the first time around, we recommended more rigorous inspection of this batch, and that's how we still found some issues, but these were by far superior to the first version, so therefore they did go on, and as far as I know, they don't have any problem. So it just speaks to the idea that if you don't get a whole lot more typically than what you ask for. So if you're going to ask someone to weld something, this is a starting point. Maybe you have in there, you want to say, oh, I want you to do some special non-destructive, and it's all in here. You can say, I want you to do ultrasonic testing, and this will have certain procedures, and then you have to say sometimes how good of a quality you want from ultrasonic, the different level, different classes of quality. So it's just part of actually getting something built. All right, now we're going to switch over to today's topic, which demand versus capacity, and that's actually how I describe my area of expertise. If somebody asks me like what I do, because I'm kind of half between a material scientist and a mechanical engineer. So when it's a question of demand, I'm not necessarily an environmental person that will, consider all the scenario that you can have with respect, bacteria or anything that is a little bit. If we talked about, say, dental procedure, I know you produce chloride, right? So these have a lot of implication to plumbing system, equipment, and all that. You need them. So that's a little bit where I stand with respect to demand, typically. How you make sure that these two are going to be happy. So what I mean demand is all the solicitation, the stresses, the environment, everything that that you subject your design or your device to. And then the capacity, I think more about kind of the intrinsic properties of the materials. So for my purpose, and that may be where people differ, if we're talking about geometry, I think of it as a demand factor, because the mechanical engineer can just say, I will avoid a stress concentration factor. So I don't need a material that will be able to deform and blunt any stress factor. So that's a little bit how I think of it, and of course there are other ways, but if we're talking about aerospace component, that's exactly how it works. You have everything that has to do all the way from the weight of the aircraft, the wind, the speed, and all the aerodynamic, going to how the connections are made, the thicknesses of the different components, give you locally what the demand is in terms of stress, temperature, environment, you name it. It gives you amplitude and all that, and then when you go to when you go through this process, you make a lot of assumptions. You have to say, okay, well, maybe I'm going to fly 10 times a day at most. Maybe sometimes I'm going to be in the Caribbean, so there's going to be a lot of salt. Maybe this aircraft I don't think it's gonna have any exposure to seawater, so I'm gonna, think about that when I select my aluminum alloy. I don't mind that it is not as resistant for stress corrosion. I won't strength. If you're looking at a space shuttle, that's a good example of that. They don't really think, oh, I'm gonna build up a lot of, salty, moist environment for years to come. I want the best strength and the temperature resistance also. So, you have a lot of assumptions there. And when you go to the capacity, it's the same thing. Okay, this is this aluminum alloy. If it's made by this vendor or this vendor, is it going to be the same? And I mentioned before about the military handbook. That's a good place to bring it back here. So what the mill handbook says, a lot of times is underestimated properties, because before you bring a value to the military handbook is where I said you need to have hundreds of tests, so it's not for everyone. It's just to get a number out of this. There's a lot of qualification that goes into saying what will be the minimum capacity of this grade of alloy with these specifications. So you can use it after the fact. You don't have to do it yourself, even if you're making airframes for original jets or business jets. So it's a good source to say this is the minimum strength. AWS is another source. It will tell you, and we'll go through an example later, it will tell you what strength is the minimum strength. So you have to put them together and not make it too much stronger than it needs to be. And that's really what overall we're going to talk about today. So there is a lot of history of development of these turbine blades for different stages, depending if you're on the compressor side. So prior to combustion, it's really not as hot, but you do have a lot of stresses, and you have particles that fly through that will, cause potential wear, erosion, abrasion. Something that is typical, not just for aerospace, but for reverse engineering, is to get the dimensions. So here, just showing a typical laser scanning system, and we're doing it on a blowout parameter, so it's not this type of component, but essentially you have a multi-axis system, and the head here is a laser that multi-focus and gets you the exact profile of the surface at very high resolution. So what I'm showing here for the turbine blade now is just essentially a rendering with just simple triangles, an STL file, very standard surface file that gives you all those profile information here. And the purpose of this project was to see, because I'll circulate this example. These blades, first of all, most of the time they are hollow, and I mentioned that because you want to pull them off with the fluid on the inside. You also can see, it went really, really bad. But that's tying a little bit, last Monday we talked a little bit about failure analysis. And when this is all disintegrated like this, it's a little hard to say how it started. So it's nice when you have multiple pieces, because you can start to see some of the differences. This one doesn't have holes. What it has is damage at the very bottom here. So, and there's one of them that is starting a crack. So I can't say for sure. I was actually not doing this one. But I would start to think that if there's very hot air, high pressure air that can start to penetrate from one end, then maybe bad things can happen. So it is a possibility. And just for my own support here, this is pretty thick wall, and if you look at this one, it's very, very thin, but it's thinned out from the inside. So something started from the inside out on this specific component. So I had questions after class last time, how do you do this, you know, how do you, so the more pieces that you can collect from the surface, the more educated you are, because they don't all tell you the same thing. This one tells me there had to be something going on in terms of the environment on the very inside of the component. This one tells me that I started, in some cases, to damage at the very bottom. So that actually goes along with the analysis I'm showing, where we had it on the computer and we were interested to look at the stresses here at the very bottom. It's the leading edge. There is always a bending force, so just from bending with this radius is where you expect the higher stresses, and from the example you can also expect some impact and abrasion of the surface. So the idea actually was to see, can we make this stronger? The original design was the one in green. Normally we try to do the opposite when we know the answer. But anyway, the green is the original design. The red one essentially moves the material a little bit ahead here. But it still has a very sharp transition. I mean, you need to turn 90 degrees somewhere, right? You start from this surface and you go to the next surface. Now, it turns out the red profile was about 30% better than the green profile, because what it meant is, you see the alignment, this is connected to the rotor here, and so the stress from the attachment goes up from this surface forward. It's going up. So if you're able to move that edge a little bit ahead, there's not a whole lot of stress risers because there are not that many stresses here. So it matters more to position the front leading edge correctly than the radius of it. You want it to be outside the main load path. And that was essentially confirmed from the analysis. Now, turns out I was working for a non-OEM vendor, so somebody that wanted to provide an alternative part to fit into an original engine. And the biggest issue was, how are we going to do it? Their idea was to use existing blades that had to be refurbished, because these blades most of the time have a safe life, meaning that they're good for a certain number of hours, and after that they get thrown away. And that's the reason why the engine is cheaper than the replacement part. Every so many hours you have to take a lot of pieces out, and that's where we started this semester. So the idea that instead of throwing it out, you will build it up to the new generation is very appealing, because they were thinking about more or less of a welding process, an additive manufacturing process to add material here. Now, I think you could probably see, and this is where these two scales are different. So this one goes to a stress of 34 KSI, and with the new design you were going to 21, and you were moving this up. So you're looking at about a 50% reduction in the stress level. That's great. If you use the same manufacturing process, I'll buy it, right? But if what you're going to do is now change the process from this very sophisticated casting to an additive manufacturing that will add residual stresses, will produce a different microstructure, is where all of a sudden my capacity is going way down. And therefore, you know, it didn't go with the FAA, and it makes sense. It's unfortunate. It was kind of a little venture they had to see, can we make this happen? And the answer was no. Of course, if you come and cast one for me, maybe I'll say, it's okay if your alloy is not necessarily the most expensive one, because now your stresses are 50% less. But the idea of changing the process, and perhaps that's where we can summarize this here, just say, in terms of the capacity, that the process makes a big difference. It really does. And that is just one example. It's very common even in helicopter blades. They have typically a composite trailing edge, and they have a metallic leading edge for impact resistance. And there are many ways you can do it. If you want to change the design, typically you end up changing both of these. You say, I'm going to use a different thickness because I've got a different property, so the demand of the material is changing, and then you change the material, so that it becomes an overall analysis, and you have to do full-scale testing for this specific example. So how do we decide on factors of safety? What is thick enough, strong enough for a given application? Let's go through the definition. There's more than one. And that's a little bit why the factor of safety will look very different to you depending on the industry that you're working in. I think the basic definition is the first one, the failure load divided by the allowable load. So the allowable load here is the demand, and the failure load is more or less the capacity. So this is always, greater than this by a certain amount. Now, it is still written in, a general form. Is the failure load always the minimum failure load? No. Is it, the average failure load? No, it really depends on the industry that you're dealing with. And it's the same with the allowable load. So in the allowable load, we talked about snow. So we had 30 pounds per square foot. We talked about people, and we were 100 pounds per square foot. We can go on. We can say there's a traffic jam on the bridge, and there's a number for that. Does that mean it's never going to be more than 30? Yeah, most likely it will, right? But it depends on how much of an area. So there is some things in code. Sometimes if you have mechanical equipment on the roof, you expect to have some drifts, and you have to say, okay, well, maybe I have a drift factor here. Okay, is this perfect science? No, nothing is perfect science in all of this. So when we think of demand, it is not necessarily the worst case scenario. I mean, the worst case scenario would be somebody decided to put a tractor on the roof to take the snow off or something like that. There's just an entire range. And when we're talking about a factor of safety, it's all, what number you're using here for your multiplication factor really depends how you do the demand and how you do the capacity calculation. And that's really what we're going to go through here. For welding code, what they do is they take a base material, and this is this stress strain curve, SN curve that I mentioned earlier in the class, where this is the life. So as you go on and you have cycles of load, this could be a bridge or anything, automotive, aerospace components, something that has even poles for electrical transmission. You got some wind load on them, and they'll be subjected to that. So what is called category A here is the base structural steel, and this is in KSI. So you can have a piece of steel that will, the range means minimum to maximum. So here you can go from minus 50 KSI to plus 50 KSI with steel, and it won't fail. But depending on what you say is going to be the number of cycles, if it's vibration, it's very, very high. If it's takeoff and landing of an aircraft, it's less. If it's going through potholes, your guess is as good as mine, depending on the region you are in this country. So when we're talking about the capacity here, it becomes a question of demand as well for the number of cycles. What is most important here in terms of the process is if you have welding, even for vibration, you're going from something that would resist more than 20 KSI to something that is more of the order of 2 to 3 KSI. And that's the factor of 10 that I mentioned at the very first lecture. And so when you think about the capacity here, I would include joining in your mind. Does it change the whole perspective? It doesn't matter If you're gonna take a very, very sophisticated steel alloy or aluminum alloy, if you go into welding, most of these properties, according to the code, any structural steel is the same strength in fatigue, regardless of what you started from. If it qualifies to be welded per this code, this is the chart they give you for all steel. So if you start really strong, but you become more brittle in the welding, and therefore they only give you the same allowable. Now, is it perfect? No, and that's why if you run an experiment, you're not going to find 2 or 3 here, because this is prescriptive, this is a design value. It's not an actual failure value. What would be the failure is actually, you know, we could do a whole series of research on this, because it will very depend on the chemistry. Perhaps some will fail at 10, perhaps some will fail very close at 5. But this is the way AWS decided to deal with all this. They say, well, in all the scenarios, it shouldn't be weaker than this amount. And then they take a factor of safety on that test result, and that is your allowable. So if you give that capacity for steel here at 2 KSI, 3 KSI, taking intention for, because you have a welded joint. What I'm thinking is, you know what, here, it's okay. I'm not going to say there's going to be, you know, 10,000 times people that are going to exceed the number of the maximum load here. So you have to take that into account. Now, this is very general, and what I want to say is how exactly you do this calculation depends on the industry. If you're doing something that's in the civil engineering world, lots of times they don't trust the soil very much because they had some bad experience with it. Over time, the soil just tends to move. So when they go to the capacity, they put very, very low properties on the resistance of the soil, just kind of saying it's a very viscous and it really won't hold itself very much. So if they start with that, and they know very, very well kind of the sea water, if it goes above the levee, there won't be more load than that. It's just going to go over. So once you have a very specific height for a levee, it's giving you the hydrostatic head that it's going to be subjected to. So when you put all these two together, you know the worst soil you can have. You take that, and then you know the height of your levee, you calculate the pressure head from that, gives you a number, only a factor of safety of 1.3. Is that great? Well, I can't say it's the best way, because now if a hurricane comes in, and it's not just hydrostatic head, it's cyclic load and all that, they didn't take that into account, guess what? We had a problem, right? That happened in New Orleans. The levees they thought had a safety factor of 1.3, did not, because of the exact conditions and how the loads were applied. Now, what did they do? They changed their way of calculating based on that. But I'm just saying a little bit here why it was very low. They thought they knew those scenarios, and then something came up in the demand and they had to modify it. The aircraft structures, I see a factor of safety of 1.5 typical. I mentioned before that landing gear is less of a factor of safety, because in everything, the landing gear is what the design engineer spends more time on, looking into all the scenarios of demand and all the scenarios of capacity. When they're done, they put a very small margin on it. If you're talking about a bridge, or we were talking about roofs a lot, a safety factor of 2 is very general, because they go through some math, but it's not absolute here, and it's not absolute based on, you know, for example, the steel joist institute. It's not going to always meet that capacity. So they do put a significant safety factor. Pressure vessel is where it's very, very interesting, because that's where they actually use the working stress. They use a lot this definition of factor of safety, which means that if you're gonna have 200 PSI steam pressure in the line, that's the number they use to calculate their demand. But we know that there will be fluctuation in that pressure when you open and close valves. There may be some water hammer in the system if you have too much liquid. All of that becomes part of the factor of safety. Instead of calculating it here, they just say, you know what, if this is a line for a certain pressure, I want a factor of 4 over that pressure against the yield strength. When they go to the yield strength in ASME, typically they will be using a minimum. They won't be using just a typical value. So they'll go from the manufacturing specs. So the reason why in ASME specs, piping system, the safety factor looks really high is because they don't go through all the scenarios of the demand. So is it really that big, the factor of safety? I think you have my answer. It's no. It just looks better if you say, oh, I have a piping system, and then when I calculate it, I got a factor of safety of 4. But when everything is taken into account with the pressure fluctuation, opening, closing the valve, water hammer, typically things are just made for the strength and safety that you need for an application. So I guess that's the summary here for demand capacity. I have the use, the maintenance, the misuse, and the abuse. And I guess that is an addition of what we talked about. We can't go through all the details on how you can think people will use what you're designing, but there's some very simple stuff that comes to mind, like if you have a handle that's big enough for me to grab on, well, guess what? I'm going to grab it. So it's better be strong enough for me and me, falling and trying to grab it. Otherwise, just don't put that handle up there. And it looks very simple, but it happens on even like little cargo carts or things that you wouldn't think are that critical. But if it's there and people can use it, if it fails, then that's the problem. Just the gripping is important. There's just a whole world about what can happen if you have something out there. Even the chair. I mean, the idea that a rocking chair you can't fall to your back still kind of makes sense. It depends, how you consider your use or done. But the idea that I'll lean back and if I go too far, all of a sudden I fall or the chair breaks, doesn't seem right. So there's just a lot to do here in terms of the demand that you have to consider. And the capacity is actually more what we focused on the past few lectures in terms of what you want and how you want it done for the manufacturing, inspection. That should all come out of your specifications. So how people think of factor of safety really, really varies from industry, but I did bring here a book that I thought had 2 or 3 good concepts. So you're welcome to borrow it. I don't read it every night. I went through it twice, and there were a few things that struck my mind, and I think I'm still using a lot when I think of factor of safety. The first thing is nothing is very absolute. So when we're talking about our demand and capacity here, did I consider all the scenario? The most typical answer is no. There is something that I'm sure I don't know. Yeah, there was some recent airplane crash. The guy decided to turn off the engine. Can you anticipate that? You gotta have one engine warning, the other's not. Decided to stop the other one just in case. You could refire both of them. It just doesn't seem right. So it's an extreme example, and it's not something that you can say the landing gear is going to resist. But you do have to say how bad of a weather, how bad of the ability of the sensor to pick up the distance to the ground, so how big the impact is going to be for the landing gear, for example. So there is always going to be a certain range that you can account for. It becomes your risk factor, it's there, you don't know how far it's tailing. So the general idea, this is capacity, and as we'll say, is the demand. You want your capacity in most of the cases to be outside of the failure boundary, knowing that you have a lot of parameters that are affecting both. So this is, you can plot this actually. You could just take a bunch of conditions. So if this happens, this is what's going to be the resulting demand and capacity. How far am I from my failure point in this condition? So it's actually not done a lot, but I think we should lead towards that because you can essentially quantify it. The best way to do it is a lot of times after the fact. If you have a lot of data about a certain model of car and how the different ways there's an incident with it, you can put it in there and start to see, okay, what is the most typical problem and how far are we from making it strong enough to resist this specific characteristic. So depending on how critical your application is, depends how big that pie is here. And that's where it becomes very counterintuitive. I have some general thoughts on that here that what people consider acceptable. This is not in any code, but it is really true. How many times there's a well blowout on an offshore platform? Several times a year. We don't hear about it, nobody wants to talk about it, but it happens a lot. How many times we have a bridge collapse? Well, not as often, because people don't like that. This is affecting the morning commute. It's very high risk, very perceivable. So as a consequence, there's a lot more regulation related to design and inspection of bridges than what's going on an oil platform, for example. It's unfortunate because there are workers on the oil platform. But the good thing here is I did not come up with these numbers. So you take it or you don't take it, but they essentially talk about what places that are really big, dams that can affect cities, levees, as something that you just want to minimize your probability of a failure. Then you come into things that are more typical, you have bridges, and then you have things that are out there, very important, but nobody is going to be there typically when they fall. So we're thinking about, say, electrical transmission towers, unless they are over a crossway, then they'll fall. You're not going to have supply of energy, but at the same time, nobody or very few people get hurt. Now that probability, of course, do depend on how long the structure is going to be there. When I make a car, and I'm thinking about corrosion, I'm thinking about fatigue, if I say, well, you know what, I'm going to make it that after 15 years people have to get rid of them, then that is helping me here in all my capacity calculation, how strong I need to make it to be for corrosion and all that. So there are reasons beyond just wanting to sell another one into specifying a maximum life for a structure. The same way with aircrafts, they'll say, well, so many cycles after 25, 30 years, you're done, I'm sorry. And then you have to find someone that's going to say, if you make these changes, you can go longer. But we do have a big fleet inventory of aircrafts that will fly, but they pass their maximum life, so they just store it out there in kind of a mild and suitable dry environment, just in case somebody's coming and say, hey, I want it for more than the cost of the material, the recycling the material. I may be able to use it for freight. So now I'm going to carry express mail as opposed to carrying people, those sorts of things. So it's really part of the overarching concept, and I've mentioned about bridges because that's something that I did work on, the bridge collapse in Minneapolis that was built in the 1960s. So no problem with the processing of the steel itself, but they did have rolling contact supports to allow for the expansion and the contraction of the bridge, and these were really rusty. So it did affect over time, all of a sudden, the demand changed. Did the capacity change? Yeah, it was rust. So that's one of the other I said there were 2 or 3 good concepts here. The concept that is very intrusive. I think everybody knows something is old, well, it's not as reliable, but there are ways to quantify that from service history, and there are very specific reasons. You know, we're talking about rust, we're talking about slow cracking, fatigue, that essentially take the probability of a failure of something. If you load it a few times, if this is a shorter service, from acceptable to not acceptable, you become below 1, and that is always true with everything we build. It's a little unfortunate, but it does happen. So, factor of safety, I showed you 1.2, I showed you 1.5, 2, 5. It really depends on what you do for the estimate of the 2 parameters. It varies from industry. The best thing, again, is you pick a method for designing car wheels, for example, and now you have wheels that have been out there for 20 years. It is your best benchmark. How you quantify the service for these wheels over the past 20 years is how you can extract some data when you completely change the design. So the data and the history here is very, very important. And I hope that you retain something out of today. I sent an email this morning. I'd like for you to think about, when we talk about material selection, I think there are a few things that I repeated 3 or 4 times with a few examples. Same when we talked about material specification. So if you can reflect and just shoot me a quick email, I'll greatly appreciate it, and I'll get back to you. Probably just expand that a little bit. We don't have quizzes. It's great because it doesn't force me to cover and put on the slide what I'm going to put on the exam and all these things. But at the same time, I hope that we get something out. We have 1 more lecture on Monday, and I will be covering more about data analysis. A lot of you are interested, so it's okay if we don't do a quiz on that one or anything that is related. So I think this should be really fun on Monday. And we have until the end of next week the class project. Again, if you're still thinking, oh, maybe this, maybe that, come and talk to us about it. Thank you.